Hi, my name is Ashley Tisdale and I will be talking about modeling a DC motor. A DC motor is an electromechanical system, which means it has an electric input and a mechanical output. The figure shows the schematics of a DC motor. It starts with a magnetic field called a fixed field that is produced by stationary permanent magnets. A rotating circuit then passes through this magnetic field. A force is thus created from this armature circuit. A torque is then created, which in return turns the rotor. There are three types of DC motors: shunt, series, and compound. DC motors are important because they can develop constant torque over a wide speed application. There are many examples of DC motors, such as elevators, conveyor belts, cranes, ski lifts, or robotics. The objective of this project was to model the DC motor and a feedback controller design via root locus. Assumptions that were made for this project were that the rotor and shaft were assumed to be rigid, the magnetic field was assumed to be constant, the friction torque was assumed to be proportional to the shaft angular velocity, the input of the system is the voltage source V, the output is the rotational speed of the shaft d theta dt. The system equations used are torque equal to Kt times current, back EMF equal to Ke times theta dot. Kt is equal to Ke, so K was used to express the constant factor. Now applying Newton's second law and Kirchhoff's voltage law, we get the first two equations. Then applying the Laplace transform, we get the second two equations. From these system equations, you get the transfer function P of S, where J is the moment of inertia of the rotor, B is the motor viscous friction constant, Ke is the electromotive force constant, Kt is the motor torque constant, R is the electric resistance, and L is the electric inductance. The spec sheet for a typical DC motor was found online. For this project, the brush DC motor 12 voltage will be used, where J is equal to 1.62 e to the negative 6 kilograms per meter squared. B is equal to 0.001 Newton meter second, and Ke and Kt are both equal to 0.011. R is equal to 1.17 ohms, and L is equal to 0.00058. To model a DC motor, I had to set design requirements. I set a percent overshoot of less than 4%, a settling time less than 5 seconds, and a steady state error of 0. The MATLAB code is shown, where J, B, K, R, and L were all found using the spec sheet for the typical DC motor. The G of S is equal to the P of S transfer function that was shown earlier. The figure step GS will give us the open loop graph. The SISO tool will give us the root locus graph that we want for the closed loop response. This is the open loop response that is received from the MATLAB code shown in the previous slide. This is the closed loop response. As you can see, the transient response is not good. This has a percent overshoot of about 30%. That is way too high. The PD was added into the MATLAB code, where the values were found using a 4% overshoot. I added grids to both the graphs, and I added a 4% overshoot. I then drug the pink dots to the boundary line, so that I could get the dampening and natural frequency values. My steady state error had not reached 0 yet, so I added a PI compensator. To do this, I took negative dampening times natural frequency divided by 10, and this gave me a 0 at negative 131, so I added this in. This gave me a final graph with everything I needed. My steady state error is 0, my percent overshoot is less than 4%, and my settling time is less than 5 seconds. To conclude, a DC motor and a feedback controller were successfully modeled based on the parameters that I set, where the percent overshoot was less than 4%, the settling time was less than 5 seconds, and the steady state error was 0.